morning, students. Today we are going to learn about relations and functions. We're going to represent the relations in many different ways, and then also determine if the relation is a function and then how to evaluate those functions. So if you will turn to page 3 in your notes packet, we will get set to go. On the first page, I would like you to write the definition for relations. Feel free to pause the video if you need more time as we go through. A relation is a set of input and output values. You can represent a relation in 4 different ways. We have, as you can see in your notes, ordered pairs, a mapping diagram, a table of values, and a graph. The ones that you're most familiar with are going to be your table of values, your graph, or if you take those and set those as ordered pairs. Remember, your input is your x value, and your output is your y. And I always remember that's alphabetical when you go through. So these are going to be the 4 ways that we can represent that. And with each relation, we want to determine the domain and range of that, which we spent a lot of time doing. Remember, domain then is your inputs, because those are your x values. And again, you can write that in your notes also. The range are the outputs, which are your y values. And we spent time looking at domain and range yesterday. And we'll do the same thing again today. In this first example, what we're going to do is take information and create the mapping, the ordered pairs, the graph, and the table and everything that's there from the information. So it says the average water temperature of the Gulf of Mexico and Key West, Florida varies during the day. In January, the average water temperature is 69. In February, it is 70 degrees. In March, it's 75, and in April, it's 78. So let's take that information and go. Well, you agree, hopefully, that January is the first month. So this becomes 1, because we can't graph January, so we need a number. So we're going to take our 1 and map it with 69, because that's the temperature. Well, then if we look at February, well, that's the second month, so that's our 2. And then that has a temperature of 70 degrees. So we'll put 70 in there. Then March is the 3rd month, so that's where that 3 comes from, and that has a temperature of 75. So we'll write 75 in our mapping. Notice the mapping just has arrows taking the x value and drawing an arrow to the y value. Okay. And then the April is the 4th month, and that's 78, so that will go here. Well, a mapping and table are very similar. You notice the biggest difference is the mapping does not, or has the arrows where the table does not. So now we just take those numbers and we insert them into a table. So we have 70, 75 in March, and then in April again we have 78. So again, mapping and table very similar. We're used to tables. Mapping, you just have to add the arrows to it. Okay. Well, now we can take that table, those values, and create ordered pairs, which then we're going to turn into the graph. So again, you've done all of this. It's just writing it all the different ways that we can represent it. So again, 1 to 69, that was already there for us. That just means January has a temperature of 69. Well, in February, we had 70 degrees as our temperature. And in March, it was 75. And April, we had 78. All right, so now we have the graph here. You will notice if we want to skip some numbers, we can put a little squiggly there on the graph. So instead of having to include or go by tens or something to make sure it fits, we can put a squiggly and say, okay, we're going to start at 68, and then after that, we're going to go by 2s. And you definitely can do that when you're graphing if needed. So now we'll plot our points. Well, 1 was going to be right there, 69. 270, so that here's our 2 and go up to 70. There's your next point. 375, go over 3 and then up to 75. And 4. And again, we don't have to connect the dots or anything. We're just looking at it. We could do a linear regression like we did the other day and see if it's linear, but for now we're just going to be looking at the representation of it. Next question now you will notice is domain and range. Well, as a reminder, domain are your x values. And we just have our dots. We're not combining the points, so we can just list these. So our x value for this case is going to be 1, 2, 3, and 4. Okay. And in range are the y values. And again, we're just going to list these because they were given to us. So 69, 70, 75, and 78. And then just put the little squiggly brackets around it. A little bit different than the domain and range that we did yesterday. With that, they were functions that were continuous. So then there we would have said, you know, for the range 69 to 78. But these are just dots, so we're just going to list them. And we'll look at graphs later today. Okay, and look at the domain and range of that. What I'd like you to do right now is pause your video and try this by yourself and see what you get. And then you can check your answer. But do pause your video and try this on your own. Make sure that you can represent it in the 3 different ways. I've given you a table, so you just need to create the mapping diagram from that, the graph, and then the ordered pairs as we go through. So, please pause to do so. So as you see, the table here is just, or the mapping, excuse me, is just a table but with arrows in between there. Now, when I would graph mine, as discussed with the last graph, is you may want to put some squigglies there. And then maybe go by 0.25. So start at 9 here. 9.25 would go right here. 9.5. And then so 10 would be here. Sorry, I take that back. We need to start at 7. So here's 7.5. Here's 8. Here's 8.5. Here's 9. 9.5. Sorry about that. And then we're going to start at 0, 10. And you notice that it is getting smaller. So 0.1 I'm going to put right here. I'm going to skip every 2. And then 0.1 is going to be way up here. Approximately. 0.2 is at 9.4, so that's a little bit lower than 9.5. 0.3 is going to be at 8.6, so that's way down here. And then 0.4 is at your 7.4, so that's really good. So you get something like that. And again, you may have created your order pairs first, which you definitely could have done. So 0, 10, 0.1, 9.8, 0.2, 9.4, 0.3, 8.6, and 0.4, 7.4. All right, now take a few minutes on this next page to write down the definitions of your independent and dependent variables. Independence variable value determines the value of the dependent. So these are going to be like our x values. This is what you're putting in to determine what y is. These are your y values. And again, pause the video if needed as you are writing this. You also need to include the definition of a function, and I would star this. This is extremely important. We want to decide, is that relation, is that list of values that we got, those x and y's, does that create a function? A function is a relation in which each element of the domain is mapped to exactly one element of the range. The big thing here is exactly one element. I think of it as that x value has one friend and one friend only. If they have more than that, it is not a function. Okay? So So again, the x value can only be mapped to one y value. If you see it has more arrows in a mapping or something like that, it is not going to be a function. If you have a list of ordered pairs and the x value repeats, it is not a function. Okay, so as we look at the bottom here are a few examples. This one, are these? Well, you look at your x values. Remember, that's our domain. And as I look here, number 2 has 2 arrows. So I always say it has 2 friends. It cannot. And so because this branches out in 2 directions, this is not a function. If you look at the next one, this 3 gets mapped to -2, 0 gets mapped to 7, 4 gets mapped to 1. There is 1 friend for each of them. They only have 1 arrow branching off, so yes, this is a function. Now, the next one sometimes can be tricky, but again, all we care about are those inputs. How many arrows do those have? So -2 goes to 5, -1 is going to 6, 0 is also going to 6, and 3 is going to 8. Well, it looks like, oh, there's a problem right here. There's not. Remember, you're looking at the x values, they are going to one value. There's only 1 arrow coming off of -1 and 0. Yes, they go to the same number. That is okay. They each still have only 1 friend. They have the same friend, but they only have 1. So yes, this is a function. And again, when I come back tomorrow, if you have questions on that, feel free to ask. Next topic to decide, is it a function or not, is looking at the vertical line test. So you notice we looked at a mapping the last time. You could think of that as ordered pairs also. Well, what if we have the graph? I don't want to list out every single point on there. So what we can do is call the vertical line test. A graph of a relation is a function if you can draw a vertical line. Remember, vertical line is up and down. And it passes through no more than 1 time or 1 point. Okay, so as you draw that line, up and down, if it only hits the graph in 1 spot, it is a function. So I use my pencil, which you can't see on my screen here. So I'm going to draw it. But really what I would do is kind of like we do with domain. Take that vertical line and move it left to right. If your pen or pencil hits the graph twice, it is not a function. If it hits the dot or the picture only once, it is. So as I take a vertical line here, so pretend this is my pen right here. Notice it is hitting at the top and at the bottom. So it hits in 2 different spots. So that is not a function. And again, I could keep going. If I go in another spot, it's still hitting twice. It only has to happen once, but if it does, that is not going to be a function. So again, it's hitting in 2 spots. It only can hit in once to be a function. Next one. If you move your pencil, so here's my vertical line, hit in 1 dot. Then I keep moving it, still hit the dot only once. I keep going. These are all of my vertical lines as I'm moving across. Again, when I come back tomorrow, I can show you with my pencil. But as you move it across, it hits the dot only once each time I move that vertical line. So yes, this is a function. Next one. Again, as I create different vertical lines, so there's one as I'm moving my pencil left to right. As I keep going, I am only going to hit 1 part of the graph. So I've only hit it here on that vertical line, I've only hit it here, and so on. So yes, this is a function. Now, why don't you pause your video again and move your pencil along left to right and determine if these are functions or not. So please pause your video and try on your own. Now, on this one, it should have been yes, no, yes. Again, as I draw my vertical line here, it's only going to hit once. On the second one, when I draw my vertical line, it is hitting the graph in two different spots, so that is not a function. This one may be a little tricky for you to see because it does look, but this line right here, let me point to it, is just getting closer and closer to 0, but it is not vertical. It just is getting as close as it can to 0 as you go. So yes, that is a function. Next topic here is something we've looked at before, but it's function notation. We had done this with piecewise, but since we're talking about functions, we're going to practice again. So again, f of x is the same thing as y. So now we're going to start using that, as I call it, fancy notation, that f of x. And then if I want to know what f of 5 is, well, this is my new x. See how it's not x anymore, it's 5? So I'm going to plug that in any place I see an x. And then you are solving this. So 3 times 5 plus 2 is 17. How do we solve it? Notice this f of 5 is just telling us that we're looking for y when x is 5. So our ordered pair would be 5, 17. We don't do anything with that 5, or that f of 5 when we're solving. That's just telling us what number we put in for x to solve. So A here, if I am looking for f of 2, that's what I'm asking for here, is then we're going to say 2 times 2 squared plus 1. Well, 2 squared is 4, so 2 times 4 plus 1. Well, 2 times 4 is 8, plus 1, that gives us 9. So our f of 2 equals 9, or you could say if we were to bracket that 2, 9 is our ordered pair. Again, why don't you pause the video and plug in 0 and see what you get when you plug in 0. I put in 0 here, 0 squared is 0, times 2 is 0, plus 1, you get 1. So that's what you should have had. Again, so that means that f of 0 equals 1, or your ordered pair on your graph would be 0, 1. Next one, I did not use a negative 2 with you, just to remind you of what happens when you square a negative. So I plug it in. Well, negative 2 squared is negative 2 times negative 2, so the two negatives cancel, so we actually again get a positive 4. And so this actually has the same answer as the one right above it. So again, at f of negative 2, we still get 9. And that's okay. Remember that it is a function here because that x value only has one answer. They do share that answer, but that's okay. Next one, I'm just going to show you this is as far as you have to go. Now, this whole item here, x minus 1, has to take the place of x. Okay, so you need to plug all of that in. So we leave the 2 that was already there. Okay, it's underlined up at the top. And then we plug in x minus 1 instead of just x. We square that and plus 1. For now, I'm going to let you stop there. In the next chapter, we'll talk about how to multiply that out and everything that x minus 1 squared. And so we'll discuss that then. It is not x squared plus 1 or x squared minus 1, just so you know. So you're done at this point for now. Last two slides are taking an application problem and writing an equation. What we used to use is y, but now we are going to create a function rule, which means an equation, but we're going to use the fancy notation instead. So pizzas cost $15 each plus a one-time delivery charge of $3. So I want to know what the cost of the pizza is, and I don't know how many I'm buying, so that's going to be C of x. Well, it's $15 each, so that's going to be my 15x. And then plus, as you guys know, is a plus sign, and then a one-time charge of $3, so I don't need a variable behind that. We just say the $3 for delivery, and we are done. So again, in the past, you guys probably would have said y equals 15x plus 3, but now we're going to use that fancy notation there and use that instead. Again, pause your video here and try this one on your own. There's two parts. The first thing I want you to do is write the function, and then I would like you to evaluate it. So pause and try this one on your own. So this one states, a cable company charges a monthly fee of $24.50, and there is an additional monthly fee of $3 for each premium channel that you add on after that. George has 4 of those premium channels. So when you write the function, you just need the first information. So you're paying $24.50 no matter what per month, but you do have that extra $3 for each additional premium channel. So that's my $24.50 plus 3x, because again, x is my variable with the number of channels. Again, instead of using y, do use that c of x. Then you had to evaluate, so that's where the 4 came in. That does not go into your function until it is time to evaluate. So then I plug that 4 in anywhere where I see an x, and it is going to cost him, for the 4 premium channels, it will cost him $36.50 a month. All right, so we've gone through the notes. Hopefully a lot of this is reviewed with graphing and domain and range and so on. But now what I would like you to do is go to your binder, go to page 5, and work on that worksheet. And complete that, please, for tomorrow.